Welcome to ECE 761, lecture number 12, Position Control of a Robot with Gears. Now the problem we're going to look at is the same one we had last time. I've got a 2-link rotational RR robot in a plane. The first link is measured from the x-axis, it rotates. The second link is measured from, again, the first link. With that, I have the dynamics of the robot. What I'd like to do is add gears, or a motor at each joint. Now, if I have a motor at joint 0 and a motor at joint 1, presumably, well, what I could do is I could have a gear attached to the motor. And what the gear does is, as the motor spins, this is 300 times, the motor spins 300 times, the actual robot spins 1 time. The reason gears are used is because motors are designed to spin. If I have a 300-to-1 gear reduction, the arm of the robot itself isn't moving that fast, but the motor is spinning. What that does is that helps increase the torque. Torque goes through the gear as the gear ratio, so I have 300 times more torque. The motor spins faster, and again, motors are designed to spin. In addition, what that does is it makes the outside world almost irrelevant relative to the motor. So when you have gearing, all I really need to do is control the position of the motor, and I automatically have the position of the robot. The disadvantage of the gearing is that the outside world doesn't affect the motor. Essentially, the motor is dead to the outside world. It doesn't know, it doesn't care what's out there, it's just going to blaze through it. So you have a robot with basically no touch. But it does simplify things quite a bit. To start out, the dynamics of a servo motor, if you work out the equations, this is a third-order transfer function. I've got an integrator. The integral of angular position gives you the 1/s. Plus I have inertia for the motor, and friction, inductance in the armature, and resistance. Typically, the inductance is very, very small, so a lot of times we assume that 0 gives you a first-order system plus an integrator. That's typical for how DC motors behave. To size the motor, I need to have a motor that's large enough to provide the power I need. One way to determine the power is pick the path you want to follow. In this case, it's a square. I want to go from here in 2 seconds out, up for 2 seconds, left 2 seconds, down for 2 seconds. Once I specify the path, I know now the joint angles and velocities. I know the torques. And the torques I know from the previous equations. Again, from here, I know the accelerations, angles, velocities. I can tell you what the torques are. Power is just torque times speed. So I can tell you what the torque is at any given point. Repeating that for tracing out the square, I calculated the torque at each joint. The blue line is the torque on the first motor. Red line is the torque on the second motor. I need at least a 15-watt motor. So to have a safety margin, I'm just going to pick a 100-watt DC motor. That'll provide enough power to follow this path. That's kind of motor sizing. The gearing is kind of optional. Power is volts times amps. If I gear it down, the speed goes up, meaning voltage goes up, but the current or torque goes down. So either way, it's a 100-watt motor. In this lecture, I'm going to look at a gear. Suppose I gear it down by 300 to 1. This is what a planetary gear looks like. The motor goes on this side and spins. This side will spin 300 times slower with 300 times more torque. And the gears are not cheap. What gears do is, as the motor spins, if this is a 300 to 1 gear reduction, over here is the motor. This would be 1/300. The robot will spin 300 times slower than the motor, or the motor spins 300 times faster. The torque is the opposite. As the motor spins, I have more torque at the output, meaning less torque at the motor. The impedance seen by the motor is torque over speed. It's like voltage over resistance. If you work it out, the torque, the impedance seen by the motor, is 1 over the turn ratio squared times the impedance outside the motor. With a 300 to 1 gear reduction, what that means is I'm going to see the outside world, the inertias, the Coriolis forces, gravity forces, so on, scaled by 1 to 300 squared. What that means is basically, relative to the motor, all I see is the motor and the gear. The outside world's almost irrelevant. So really the whole goal is control the position of the motor. There's a couple ways to do that. Here, if I have a motor, this is the Pitman motor. It's going to be roughly this transfer function. I'm going to add a compensator. What I want is the angle to follow the set point. This is my desired angle. That's the path that traces out a square. A couple ways to design the compensator. If I just use proportional control, meaning this is just a gain, what I'll wind up with is the angle is your transfer function, 714 over s plus 162 times p. That's your peak control, just a gain. Close the feedback loop, I get gk over 1 plus gk. Here's what I get. I want this to have a gain of 1. It doesn't. At DC, the gain is 1. That's good. At high frequencies, S is no longer 0, and the gain becomes less than 1. The step response with the proportional feedback looks like this. I've got a delay in the system. And it's supposed to be 714p in the numerator. I can see that in simulation. Here, this is the simulation RR gears. I'm going to trace out a square. That's with a spline curve bit to find where the robot's supposed to be. Then here's the motor dynamics. This would be 100 over s squared plus 10s plus 100. What that does is the motor angle, the dark blue line, lag behind the actual angle by this transfer function. And that's the transfer function of the motor. This assumes I've got gearing so that the robot dynamics really don't matter relative to the motor. With proportional feedback, I have a delay, and you can see that in the transfer function, the numerator and the denominator don't cancel. I've got this s squared plus 10s that don't appear in the numerator. And that's what you get here in the step response. That causes a delay in the transient. Second type of feedback is PD control. If I can measure the velocity of the motor and feed it back, what that does is that adds the second term right here. I can make this derivative term larger if I want. What that does is I can get a quicker response. And essentially what I'm doing is this factor of this polynomial, I've got two real roots. If I increase this term right here, I can bring the roots together and maybe get a double root or a root with an angle of, say, 45 degrees. In terms of the simulation, that'd be just change this middle term right here with PD feedback. If I take this guy, this has roots at s squared amplitude is 10 and 45 degrees. This has poles at -7 plus minus j7. What that does is a little more friction actually speeds you up a little bit. And now you see the actual angle, the dark blue line, is following the desired angle a little bit better, less oscillations. But it's still lagging. The problem again is the numerator polynomial doesn't match the denominator. A second version of PD control is if I can essentially measure the velocity of the set point, then instead of having to put in just the position, I can now take ds times r. I'm going to have the feed forward term, the derivative of the set point. What that does is I can now take ds and p and have it cancel with this s plus 162. And then just have a 714 over s, close the feedback loop. This is what I get. In terms of the transfer function, what it looks like is I have a 14s plus 100 over s squared plus 14s plus 100. These two terms cancel. All I'm left with is an extra s squared in the denominator. That feed forward term, that 14s, causes much better tracking. But to do that, I need to know the derivative of the desired angles. That also shows up in the set point, or the step response. Again, it's much faster, and so we'll have better tracking. The last case is if I can feed forward the second derivative. So this is your PD control we had before. I just added a DS term. That gave me the 14s plus 100. If I can feed back the second derivative of d, that what I wind up with is the numerator and denominator cancel. That gives you gain of 1. That means that theta equals r. If theta equals r, I've got perfect tracking. So I get basically step response is 1. In simulation, that shows up as the transfer function being s squared plus 14s plus 100 over s squared plus 14s plus 100. These cancel, so the gain is 1. When I have a gain of 1, the desired angle, the light blue line, is equal to the actual angle, the dark blue line. And that's pretty much what the homework is for homework set number 12. Trace out a shape, like a star, triangle, pick your favorite shape. Find the motor angles, velocities, and accelerations, and then filter them like we did here. If I have proportional feedback, I just have the one term. PD, I've got two terms. PD with feed-forward acceleration gives you the three terms. And then I'll have ideally perfect tracking. That's what you can do with gears. With gears, you kind of ignore the outside world. All I want to do is control the angle of the motor. If I can control a motor's angle, I can then control a robot. That's lecture number 12 for ECE 761 Robotics.